Morning, guys. So yesterday we had ended off looking at that virtual simulation. We rebuilt the circuit that we had calculated through. We put in the battery that supplies the voltage. It supplies the energy to those charges. We found that those charges, parts of the circuit were actually in series, so all the current had to travel through that one top resistor there. And basically, every time it encounters a junction, the charges have to decide whether to take down one path or the other path here. The load in our case here could have very well have been just resistors. They're just a little bit more interesting if we actually put them as light bulbs. Light bulbs themselves will actually slow down the charge. Will actually, in resisting the flow of electrons, it actually is able to convert the electrical energy that those electrons have to move through back into light energy. We also talked about having our 2 meters. So we had our voltmeter. Voltmeters themselves have very high resistance. You put the 2 leads here on either side of your each component. It could be for the battery, it could be for the light bulb. And basically what it tracks for you here is by adding it in parallel, it actually tracks how much voltage is actually either supplied or gained by the battery or is used up by each particular light bulb. It becomes very convenient, so we're not actually having to do a lot of Ohm's Law ourselves. The other meter that we had was called an ammeter. An ammeter by itself has very low resistance. You actually put it in series, whichever branch or whichever path that you're taking, and as electrons flow through the ammeter, we actually get a sense of how quickly those charges themselves actually move through, and that actually senses the current as well. So what we're going to do here is we're going to start off with another circuit. I'm going to play around with some of the variables here, just getting you practice with the problems. And then today we're going to use the lens of introducing power again and introducing energy. We have actually seen these back in an earlier chapter, but we're going to specifically apply them to circuits in this section. So let's have a look here. Let's pretend we have a battery circuit. Remember, the long line here is positive, the short line here is negative. This time I'm not going to give you the voltage of the battery just yet. I'm going to introduce here, we assume conventional current, or I, are positively charged particles that leave the positive and flow positive negative. I'm going to introduce a junction here where down the first branch it actually encounters 2 resistors. For these 2 here, what I'm told is for this bottom resistor, this bottom light bulb here, maybe I stick a voltmeter across it, and I realize this bottom resistor uses up 6 volts worth. And we know that the amount of resistance here is actually a 4 ohm resistor. So that's going to be our second resistor. So far, this is just one series circuit. Any cars that arrive at this junction also can take the other pathway. Again, we call this a branch. It can take another pathway here. For this one, maybe I've used the ammeter or some sort here. Notice where my ammeter is placed is only down this branch. So I'm only sampling the cars that actually travel through this one. The ammeters, let's just call this one here, R1, R2, and R3. So ammeters measures current, so I can say maybe I3. Let's say the ammeter gives me a reading 3 amps goes down this pathway. And this resistor itself is also a 5 ohm resistor. I think that's all the information I need to give you. Basically, if I haven't listed it for you, we can look for those things. Can you find for me what's the voltage of the battery? What's the total number of cars considering both pathways? What's the resistances we're going to work our way through? Pretty much, the formula is going to end up being Ohm's Law, but you just need to remember for Ohm's Law, you need to apply it to each particular component individually. So what's happening here is, let's say I do Ohm's Law here. I know a lot. I know the speed at which the charges are going through is at 3 amps. I know it's trying to travel through a 5 ohm resistor. I can just go V is equal to IR. I can multiply the 3 amps, multiply by the 5 ohms, and this tells me, oh, through this light bulb here, or whatever load, buzzer, or whatever it is, it actually is dropping by 15 volts. It's actually converting the electrical energy back, if it was a light bulb, into light energy. So that was 15 volts. If I look at Kirchhoff's loop rule, it said basically by the time I arrive back at the slide, I better have used up all my voltage. I picked up some voltage from the battery. If I consider the particles that travel through the bigger loop, so travel through this red branch, red pathway, I only actually end up traveling through the one resistor. If I'm able to lose 15 volts before I get back down the slide, how much voltage did the battery have to supply you? Well, in that case there, great. We now know the battery is now 15 volts. That's the advantage of sort of doing the loop rule here. Around any loop, we have to make sure we've used up all the voltage. Now what I can do here is the more information I get, I can keep finding the unknowns here. For the first path here, I actually know for the second resistor. Now I don't know the whole voltage going down just yet, but I do know the resistance and I do know the voltage of this path. anytime you have 2 out of the 3 variables, you can do Ohm's law. V is equal to IR. This time what I know is this light bulb by itself, just the R2 resistor, it uses up 6 volts worth of energy. I want to know what's the current, as the resistance here is a 4.0. The current down this path here is actually 1.5. Again, to be sure, current is best interpreted. Oh, it's actually the speed at which it goes down this path. I'm noticing here, well, the speed going down this path, any cars that go down this resistor would have also gone through the resistor number 1. I now know that 1.5 amps, 1.5 worth of cars actually go down this pathway here. I'm just looking in total here, only 1.5 go down this way, but 3 amps go this way. Roughly speaking, I'm going to assume that this total resistance here is a little bit higher. That's why more cars decide to go down the other pathway. Again, the more correct interpretation is cars that go down that pathway can travel faster. But there we go. We get more information here. We can use Kirchhoff's junction rule, and we can say, well, we have 1.5 amps going down one path, 3 amps going this path. In total, 1.5 plus 3 amps is 4.5 amps. That means I had to have a total amperes of actually 4.5 amperes, so that when they divvied off, 1.5 went down that way and 3 amps going down this way. Usually, if you know that total current, the whole problem falls apart. I can do equivalent resistance again. I can figure out what the unknown resistor is. This time, the question is a little bit easier. Let's just use the loop rule one more time, and let's say, well, if I know the battery supplies 15 volts, I know somehow after using the first resistor, second light bulb here, I know by the time I get back, I also need to use up 15 volts. If I know the second light bulb only used 6 volts, I can actually calculate 15 minus 6. That means it has 9 volts left to use in this resistor. Because I'm having to use up more of the voltage, I would expect the resistance a little bit higher. Let's see if that's true here. Again, the more you know here, you can just use V is equal to IR. The formula, again, is exactly the same all the time. Our voltage in this case here is a 9-volt battery. The current is 1.5. Let's figure out what the unknown resistance is. If you solve your way for R here, R would equal to, I think it's 6. 9 divided by 1.5 is, perfect, 6 amps, so 6 ohms. So there you go. I just wanted to demonstrate to you here, we are basically using Ohm's law again and again, but what's happening here is I'm using Ohm's law for sort of each component one by one. Anytime I know 2 of them, I can figure out what the third one is. All right. Today I'm going to introduce to you one last formula, which is power. We've learned back in our energy unit here, power is actually defined as sort of the change in energy divided by change in time. There's a job that's going to take a certain amount of energy. You can frame that in terms of work here. But what power measures is power says what's the energy in relation to how long it takes. So your task may be, oh, I want to boil water. If I have a very powerful kettle, I can accomplish that same task in a short amount of time, a high power, a high wattage kettle. If my kettle here is not as high power here, it's going to take longer time. I might still eventually be able to transfer that total amount of energy to accomplish the task, but because it's taking much more time, the power itself rating is a little bit lower. As we look at sort of power in the context of circuits here, even though this power, I'm going to reuse this formula in a second here, in the context of circuits here, when we're actually looking at current, when we're actually looking at voltage, for circuits, this is on your formula sheet already, how power is actually worded, power is actually defined as I times V. If you can somehow, so sort of in the application of circuits here, power is given by the current, it's given by sort of how quickly your charges can flow through, current is measured in amperes, and it's also a product multiplied by the voltage. The voltage is sort of how much energy do these charges carry, how much energy am I reconverting from electricity back into light energy. So that's going to be volts. So if you have that lens there, basically, oh, all we need is just the I times V, and I can actually come back and I can figure out the power. I can figure out how quickly the energy is actually transferred back. In this light bulb analogy here, it's going to actually tell me the brightness of the bulb. It's going to actually shine brighter if I have charges moving quicker and it's actually converting more of the voltage back. So because I actually have all these values, right, I have current, I have voltage for all these ones here. Let me just resketch it on the outside so you can see it a little bit better. I have a 15-volt battery. We said going down path number 1, we had already calculated here. If I had an ammeter, it was 1.5 amps. The voltage through the first battery, for the first light bulb was 9 volts. The other one here was 6 volts. Going down the other pathway here was 3 amps worth, and this was going through a resistor which is 5 ohms. 5 ohm resistor, so the total voltage is 15. Right? I had already found these. Because I actually have an I and a V, I can actually ask you what is the power at each of these light bulbs themselves. So let's just practice going through the formula here. Well, what's the power? Just like Ohm's law was applied to each circuit component one by one, power is also like that as well. So for power here, I can say, well, I have 3 amps worth of speed. I'm going to use up all 15 volts that I got from the battery. My brightness is actually going to be 45 because it is power. I'm going to remind you the unit is W. W is a watt, and a watt is actually a joule per second. After every second, it actually delivers this many joules worth of energy. Because I have the I and the V for these other ones here, I can also do my power formula. P is equal to IV. So the current is a little bit slower, right? Overall, this resistance was a little bit higher. 1.5 amps, but I'm going to use up 9 volts for my first battery here. Let's just punch our way through here. 1.5 times 9 gives me 13.5 watts. I notice that this number here is not as big as the other one, so this one here will be a dimmer light bulb. And then the other last light bulb here, power is equal to I times V, 1.5 amps, so that's the speed at which it goes through the first resistor and the second rough patch here. 1.5, the other voltage, I only have 6 volts left over, so this one will even be an even dimmer light bulb. 1.5 times 6 gives us here 9 watts of energy, so 9 joules worth of energy. So this is how you address questions on the brightness of the different bulbs here. The higher the power, it can deliver more energy in a shorter amount of time every second. So this one here will be a lot brighter bulb than, say, this first bulb here, which is the second bulb here is even dimmer than the first bulb here. We can actually track the brightness that way. Just a little mathematical trick here. Because power in our circuits unit here, so we're applying it to the application of circuits here, because power also deals with formulas like I and V, well, I know another formula that has V's and I's and R's, whatever. In this case here, it's called Ohm's Law. Well, wherever I see V, Ohm's Law says I can actually write that as IR. So sometimes, depending on the problem, you might not know all the I's and V's like I did in this question, just for simplicity. What you can do here is you can say, well, what if I subbed in Ohm's Law instead of V? What if I thought of that as I times R, which is why power can also be worded as I squared R. So if you happen to know the current, I'm actually calculating the voltage if I take the other I and multiplying by the R. But sometimes I just know current and I know the resistance. So for example, I know the current is 3 going down this path and the resistor is 5. I might not know the voltage right away, but I could go, what's 3 squared? 9 times it by 5 is equal to 45. That also gives you power without actually calculating over for voltage itself. There is the one other derivation as well. Both of these are in terms of I so far. I would need to know the current. What if I don't know the current? What if I replace the I here? If you did Ohm's law, V is supposed to equal to IR. I'm going to isolate for I. I is equal to V over R. So wherever I see I can actually punch in V over R. What if I took this power formula, P is equal to IV, and I actually put in V over R instead of the I? So what we're going to get here is we're going to get V over R times V, and in a similar fashion, I'm going to get something being squared. So now I actually have 3 different ways of writing power. They're all based on the same formula. Power is given by an IV, but by applying Ohm's law, by rearranging that term back in, we now have another relationship. Power could be worded as I squared R, or power could also be worded as V squared over R, just depending on what variables you have. In general, as you saw in this question, the more you know, you actually have more ways to actually solve for power. Right? So that actually has to do with brightness. In this section here, they can start introducing to you, well, what if one of the light bulbs burns out? In this case here, if a light bulb burns out, it effectively cuts off that circuit. So we already talked about in Christmas lights here. Let's say if I'm out of luck here, let's say this 9-volt battery here burns out. If that burns out, the tungsten filament here totally cuts off the circuit. It totally cuts off this pathway, and now even the other bulb will burn out. We talked about if it's in series, it just burns out all of them in one row. You would imagine then here is, well, the brightness of the other bulb would change. Suddenly we went from being a parallel circuit, and now we're basically a series circuit. Yes, I know these are physically still there, but because they're not connected anymore, electrons will not go down this pathway. What we can do at that point there, it's actually a little bit more confusing than we're thinking. So we have the voltage from the battery. Let's say in that example, this first bulb burned out. So I still have 15 volts from the battery. I only have the single path through the second resistor. Just double check my numbers. It was 5 ohms worth. At first, I had said, well, easy. We have 15 volts being used up by the 5 ohms. What's happening here is you need to be careful. Remember, electrons have that ability for foresight. They can actually figure out the total number of cars at first was 4.5 amps. They can actually figure out what's actually up and coming, where the total current may actually be different depending on what's coming up. So if we consider what's sort of left over from the circuit, what if I had the same 15-volt battery, the other pathway here has sort of died out, that pathway is no longer available, the resistor hasn't changed, it's still a 5 ohm worth of battery, what is the total current coming off of it now? Well, the total current here is given by V over R, that's just Ohm's law. If this one here has to soak up all 15 volts, I divide it by the resistance of 5, you actually realize that the current here is just the total current of 3. Earlier, the total current was actually 4.5. It was actually divvied up between the two. In this case here, only 3.5 actually want to come out of the parking lot at first. And you'll notice that even though it's same battery, same resistor, same everything, the total current may actually be different before and after. We'll see that a little bit better when we actually do this on our simulation. But just be really careful. Every time you start removing components here, you need to do a recalculation. Has anything changed with the total resistance? Let's say I had a light bulb, I don't in this case, but let's say I had a light bulb sort of early on. My light bulb would have had 4.5 amps because there's more current that comes out if both paths are available. In this case here, if I had that very same light bulb, I only have 3 amps worth, the brightness would change just because the total resistance of the pathway has actually changed as well. I could do a similar analogy here. Let's say the other light bulb has burnt out. Because that parallel has burnt out, parallel paths usually decrease the total resistance. That's what actually made this overall current a little bit higher as a number. I would imagine if I just did that, if I burn out this path here, I'm just series through just these 2 light bulbs here. These 2 light bulbs here are still burning really bright. In this case here, I'm still going to use up the same 15 volts, but again, the total current may not any longer be 4.5. It may actually be less than that. I'm going to do that on the simulation so you can see it better. Let me do just one last thing before we switch over to the simulation. It's nice looking at this power concept here. It's I times V. We can track the brightness of the bulb. We can introduce this question of sort of when one bulb here burns out and whatnot. Because power at the end of the day has to do with energy divided by time, I can actually figure out, well, how much energy I'm actually using for my in my everyday life. And usually for us in BC, we have BC Hydro basically charging us or billing us for how much energy that we use. So just one other little switch to the problem here. Pull up my electricity bill so you can see sort of how this works out as well. We can finish off with using the lens of energy. Energy, we're going to use E for it. So far, we've used power is equal to work divided by time. Remember, for work, sure, it's force times distance, but the easier formula was work is causing a change in energy. So in this case here, I'm going to say power is actually equal, let's just put in, it should be change in energy over time. And because BC Hydro is going to be charging me for the energy that I use, I'm just going to isolate for this E. I'm going to bring this T term up. So the energy that's being used is going to be, quite simply, what's the power rating of your devices and how long do you actually run that device for. So when you go shop for appliances here, usually a more modern device here would have a better power rating. It'll basically tell you for every second how many joules is it able to deliver. The overall energy that I use depends on how long I actually run the device. So the time on. And I'm just going to pull up my BC Hydro bill here so you can have a look. Relatively speaking here, in BC we don't really pay a lot for electricity. Usually every 2 months or so, they basically come in. They used to actually send people around to different households. You would, maybe if you have a house, you might have a water meter on the outside. Nowadays it's a lot smarter, so it can just automatically track it. They don't need to actually send a person around. But what they would do is they would take a reading here. This is the last time they billed me, which is February 21st. They said the meter actually read 9312. Now, they're not charging me directly 9312 because I've already paid that amount. What they're doing here is they tested it at February 21st. Again, roughly 2 months. It's kind of strange. Sometimes it's a little over 2 months. I don't know how they actually do the billing. I guess they sort of separate it so it's more manageable. But they basically come a second time. Again, now it's all smart meters. Now it's all automated. And what they do is they read what my meter says for my power consumption. And what they're going to bill me for is just the difference in energy. How much energy did I use between February and March 31st? So what they did here is they did that subtraction, and they realized, okay, the amount of energy that I used was actually 234. They actually have this energy rated with a funny set of units here, which is a kilowatt hour. We can use dimensional analysis to sort of figure out that is an energy quantity here. Kilowatt here would have been a unit of power, and they're multiplying it by time. So power times time gives you a measure of energy. Why don't they use joules, which we're used to? Again, unfortunately, here in this context, the joule is actually would be a humongous number. I'm just going to show you the conversion here. What if I just had 1 kilowatt hour? So let's think about this here. I'm going to have my device that's rated at a kilowatt. So that's going to be 1,000 watts. And it's actually multiplied by time for every hour that I have this device on. Now, I don't have to have it on consecutively here. Remember, they're billing me over the 2-month period here. But basically, it's how long did I have that on? So let's just track this here. 1 kilowatt is equal to 1,000 watts. We know 1,000 watts is actually 1,000 joules for every second. An hour, I know, so it's going to be that multiplied by 1 hour, right? That's what a kilowatt hour is. It's not per hour, be careful, it's multiplied. For 1 hour here, you can do it in your head here. 1 hour is 60 minutes. 60 minutes has 60 seconds. So 1 hour is actually 3,600 seconds. So what it's actually doing, by designing the unit kilowatt hour, you notice that the seconds here cancel out. 1 kilowatt hour is actually equivalent to 3,600,000 joules. So the joule energy, the SI unit that we like, happens to be a very, very small number. If they gave me my billing here, oh, here's how many joules I use, this would be in the billions. This would be in this like 230 million, something like that. It'd be a huge, huge number. By doing this conversion here, you can just treat this as a equality here. 1 kilowatt hour we just derived is equivalent to 3,600,000 joules. It's just another way of reframing the energy unit. So again, looking back at my bill here, I happen to use 234 kilowatt hours during this 40-day period. They'll actually give me a lot of statistics with how much did I use in comparison to the last 2 months, how many did I use even this time last year, because sometimes our energy consumption, usually in the summer times, we're not paying for heating, things like that. Usually the energy bill goes down. Usually in the winter times when it gets cold, you're cranking up your heaters and all that. Usually they sort of track this rise and fall. And I'm just going to show you sort of the details of my bill here. This is my most recent bill. What they're going to actually do to encourage people to actually save energy, they actually bill you on 2 steps. So the way I think about it here is sort of there's a staircase diagram. There's a certain limit here that basically says the first amounts of energy that you use is going to be charged at step number 1. Step number 1, they're actually charging me here, it's about here 9 cents for every kilowatt hour that I use. If I overshoot the threshold for step number 1, for step number 2, you'll notice that the charge goes up. It's almost 150% more. But they do have a threshold. So let's read what the threshold here. It says 996 below the threshold. The overall threshold was 1354. So I have 1354 kilowatt hour worth of room. So what would happen here is, let's say during the 2 month, in this case here I'm noticing it's actually 40-day period. During that window, if I used, let's say 2,000 kilowatt hours, which I didn't, right? That's a humongous amount. What they're going to do is they're going to say, for the first 1354, I'm going to bill you at the lower rate here of about 9 cents for a kilowatt hour. And that's where they calculate, here's the energy you actually used here, 1354 times it by that charge here, they would have that money. Again, I didn't use anywhere close to that, so that's why I only have 234. The difference, however, if I use, let's say 2,000, I minus off 1354, the rest, 646 here, wow, you used a lot of energy this month here, they're going to charge you the difference, 654, at that higher rate. They would have said 654 multiplied by a higher cost, and that's actually going to amount to the other part of my bill. So again, they're trying to encourage people to save money. They're encouraging people, try to keep your power consumption at least in step 1. We're going to bill you for less of it. It's not that you couldn't use that energy. It's just note that if you overshoot that threshold, even this threshold changes a little bit from period to period. But they're basically trying to say, if you can stay in this low consumption, I'm going to bill you a little bit less. If you overshoot that, I'm going to actually start charging you a little bit more for it. There's some other levies and whatever and whatnot. There's GST on the bill, and basically that's how they calculate the bill. So if you're interested, you can talk to your parents. You can see, well, can I see a BC Hydro bill, and can I understand how much energy we're using? Of course, we want to be environmental, not just, oh, let's save money by saving energy, but also let's save the planet by saving energy as well. So what we're going to end off with here, I'm going to go back to that simulation. I'm going to rebuild the circuit that we just created. We're going to answer that question of brightness and see how we did with our numbers. Okay, so we're back on our simulation here. Just before we actually rebuild that circuit there, I just want to show you some other tools at your disposal. This was our toolbox. We've been using the wire, battery, light bulb, and whatnot. You can actually toggle this arrow downwards. Some of our houses, we have in our circuits what are called fuse breakers, and basically these fuses here are designed if you accidentally turn on too many devices and they happen to be on the same circuit. By drawing too much current, it can actually pose a very safety risk. It can actually cause things to overheat, cause things, electrical hazards, fire hazards, things like that. These fuses here are designed if you accidentally draw too much current, the fuse itself will break. It's like a switch that permanently switches off. It will definitely cut off all your devices right away. You can figure out, well, oh, how come my devices are off here? Oh, again, it's a safety feature. Most houses here will just have fuse breakers. Once you've guaranteed that we're safe, right, turned off the device or whatever, you can just flip the fuse breaker back up. You can let the current naturally flow and then know for next time, oh, let me not run the microwave and the stove and the kettle on at the same circuit all at once. You can also play around with other things here. We like using things that are conductive, like wiring, metal of a paper clip here. They actually let you in the simulation play around with like a dollar bill, eraser. Those are called insulators. Those don't actually let charges flow really freely, but you could introduce those in the circuit here. You could have your hand or your dog, although I wouldn't encourage it here, but I guess in the virtual environment, why not? So let me just build this circuit here. Let's start off with our battery. I'm going to try to match it up as much as we had on our circuit. Our battery here was a 15-volt battery. That could be just a single battery, or it could be maybe 5 3-volt batteries all at once here. Sometimes when you click it, they may give you the snip option. It'll basically disconnect it if I had anything attached. So far, I don't yet. I'm going to keep my circuit diagram as perpendicular as we can. In fact, in this case here, I want to show you something with the ammeter. So ammeters here themselves have really low resistance, but they have to be connected in series. Let's just connect them here. I'm going to build down the first pathway. I could really just use a resistor. It would do the same sort of conversion, electrical into just basically the load will use up the energy. It's much more interesting when I actually stick on a light bulb. I'm going to connect that there, see if I can twist it down. Make sure as you're building your circuit, you do connect it to different sides of the light bulb. Don't accidentally hold the wire to the same end. So we have 2 light bulbs here. So those are 2 resistors down the first path here. I'm going to connect the remaining here. So far, if I pretend I don't even have that parallel pathway just yet, this would be a circuit in itself. Kirchhoff would say, well, if I gain this much voltage from the battery, 15 volts, by the time I get back to the bottom, I have to use up all 15 volts here. There we go. It's running both of our batteries. I want you to note down this current right now. The total current of the battery, electrons have that ability of foresight. They know sort of what's upcoming. They know sort of overall what speed they can travel through depending on sort of the resistances in front of them. What's going to happen here is I'm going to introduce my parallel path. So I'm going to create that junction here. You'll notice there's no way after it, so the electrons won't flow in that direction. It's only when there's a complete circuit that we can actually flow. I'm going to build on my last light bulb here. So let's stick the light bulb on there. And then we can just complete the circuit here. What I want you to watch for here is what happens to the total current. It's not as simple as we make it seem here. Well, yeah, the total current is 0.75. Yeah, so what? You attach another parallel path. We know in general, as you increase more options, more pathways, it actually lowers the overall resistance. You can verify that using your R1 plus R2 for series formula, 1 over R1, 1 over R2 for your parallel formula here. If the overall resistance is less, I would expect that the total current would actually go up. So currently here, if we have just the first loop, we only have 0.75. The speed at which the electrons are actually flowing, or conventional current positive or negative, is only 0.75. The second I make a detour, even if this pathway here is a not as ideal pathway, we'll notice that the overall current actually does increase. So every time we do something to the system, especially as we deal with this light bulb burning out situation, it's not so easy just to take our numbers, oh, that's the current from beforehand. Well, as things start burning out, maybe the total current from the battery is actually different. I actually need to go and recalculate it here. So what I'm going to do here, just for convenience, I'm going to stick my ammeter. Just for completeness sake here, I'm just going to put down the current meter. I could have actually built in an ammeter. I guess this is a little clever. Just be careful, ammeters do have to be measured in series. So like this one here I showed, it actually does have to be in the pathway. Just before I deal with that sort of light bulb burnout analogy here, let's make these resistances what we had on the notes. So this first one here was a 6 ohm resistor. If you can track the brightness as I'm changing this here, that's 6 and this is 10 ohms. Let me track this down to 4 ohms. As I decrease this one here, you're going to see slight changes already with what happens to the brightness. Just even right now, if you look at it here, I don't know if you can see it, because we have a, in this case, 6 ohm resistor, a 4 ohm resistor here. The 6 ohm resistor is going to use up more of the voltage. If I go I times V, it's actually going to give a slightly brighter light than this one here. I can even dramatize it here. The bigger this voltage is, well, if more of the voltage is used for one light bulb, not the other one, although both light bulbs are still on, when I go I times V, it's the same current going through this one pathway, but because the voltage here is a lot higher, it's going to be a lot brighter. So again, back down to 6 as we wanted it there. On the other side here, we had a 5 ohm resistor. So knock this down to 5. You'll notice as I change the resistance on this one here, it might actually affect the brightness on the other one. So far this is what we have. We have the yellow streaks here showing you how bright these light bulbs. We had calculated the power on this one here was the dimmest bulb. This one here converts more joules per second. This one here converts the most, because if you imagine for the parallel path, I have all 15 volts available to brighten this bulb here. If you track that there, again, we have 3 amps worth of current, no problem. Just before we deal with the burnout example, there are 2 other things you can play around with here is the wire resistivity. I mentioned every time you put a component here into the circuit, it adds a little bit of resistance. Now we usually ignore the resistance that the wire itself takes. It's a conductor. It carries charges really well. It's possible that the wiring itself may actually have some resistivity. Maybe the wiring itself slows down the electrons. You notice again the total current has changed. We can go from lots of resistance, slow down the current, but pretty much we're only going to do really tiny, as if the resistance is 0. The other thing here is you can do the battery's resistance. We talked about here, I had set the voltage here to be 15 volts. That's the true EMF. This is assuming no internal resistance. As I do start getting some internal resistance, as the charges migrate through the battery, diffuse through the material itself, it actually slows down. I'm going to lose some of the voltage. If I pull up my voltmeter, I'm expecting this one here will be something less than the 15 it should have been. I had qualified it here to be a 15 volt battery, and yet if you look at the voltage left over, given the internal resistance, I subtract off the I times little r for internal resistance, the overall terminal voltage is actually decreased. We can even switch over here to a circuit diagram here. So they do the long line for the positive side, short line, battery. These are light bulbs. I would probably introduce a switch of some sort, so that way I'm not running this at all times. Let's just visit the very last question here of that sort of light bulbs burning out. Let's track the battery resistance to 0, no resistance on the wiring here. Let's go back to our light bulb analogy. So let's do the burnout here. I want you to again track the total current here. The total current was actually a little bit higher because I had this parallel pathway. What if this light bulb burns out? What if that tungsten filament basically breaks off? As it breaks off, it basically completely cuts out the parallel path. Now I'm down to all the electrons having to go through this rough patch here. You notice the total current coming out of the battery is actually less. There's less cars that actually want to come out of the battery because there is only one way around. Whereas when that light bulb was actually there before it burnt out, I had some 4.5 amps worth of current. So be really careful every time we deal with this burnout analogy here. Yeah, factor in, oh, after it's burnt out, that path is no longer available, but then do a recalculation. What's going to stay the same is the battery voltage. The resistances are going to stay the same, but usually the total current, again, the circuit components here have this nice foresight. They actually know what's upcoming. If I know I have the parallel path here, more people are willing to come out. If I have lost a path here, less people are willing to come out. So I realize I don't think, oh yes, I need to convert this back to 5 ohms. That's why the numbers were a little bit different. All right, so that was a burnout analogy here. Definitely the bulb that burnt out definitely is not going to be bright anymore. In fact, this one here, the other bulbs here will actually change brightness. Not only will the total current change here, the overall brightness, I just want you to track these streaks here. If I delete this light bulb here again, you notice that, oh, in this case here, I guess the relative resistances were very close. We're going to see a little bit better in the next example here. What if I burn out the other side? So there's my light bulb. Let's hook it back down to 5 ohm. That's what we had. And then let's delete one of these other light bulbs. Let's say that filament burns out. Once one of the filaments burns out, that path is no longer available. If this bulb burns out, it's actually going to cut off both of these light bulbs. So I'm going to delete that there. Let's track this total current again, which is 4.5. When one of that light bulb burns out, again, my total current has changed. Now I only have a series pathway through here, and I don't know if you were able to see any change with the brightness. Let's put that light bulb back in. As that light bulb was back in here, right? Not only, okay, when one light bulb goes out, both light bulbs go out. Let me see if I can change the resistances in such a way, sort of different from our diagram, but so that you can see maybe a relative difference in brightness if I tweak it one way or the other way. Just track sort of the size of these streaks here. As I delete this light bulb here, you might find that these streaks here also change. We definitely see that in terms of the current change here. So every time we have one light bulb burns out, I want you to recalculate for what's the total current now, because those electrons know what's upcoming. They don't no longer have a parallel path. They only have the one pathway. And then what's an I times V, or I squared R, or V squared over R? It's the voltage and the resistance don't change, and sometimes it actually changes the brightness. Right? So play around with that simulation, work through your worksheet a little bit more, and then on your assignment, you actually get to build some of these circuits here. Thanks, guys. Take care.